All right, back again. This time we're going to take a look at our last section that deals with quantum mechanics. So here we are, finishing up our quantum mechanics notes. This is going to be section 4.4, and we're going to look at exceptional electron configurations. So we last time we took a look at some different rules that kind of govern how the electron configurations are done, and this time we're going to take a look at a few times you break those rules. So the idea here is that some configurations are more stable than others. And so because they're more stable, we get to kind of break the rules in order to achieve those configurations. So number one, the most stable. Our first place winner is always a full level, and that looks like P6. So it doesn't matter if it's 1P6 or 2P, well, there's no 1P, but 2P6 or 3P6, everybody in this family right here all ends in P6, and they're all the most stable an element can get right here in P6. I don't know if you remember the name of these guys, but we call these guys the noble gases. They don't react with anything else, or very rarely will they react. Why don't they react? Because they've got P6. They've got the best electron configuration there is. They've won. Why change that? So that's P6. It's the first best place to be. There's a second best place to be as well, a second place winner, and that is a full sublevel. So if electrons can get to a full sublevel, that's a good place to be. S2, that would be a full sublevel. You are filled up at the S. D10, good place to be. Second place winner there, D10. And also, if you can, we won't work much with this, but F14, good place to be. You can fill those sublevels. That is a good place to be. S2, D10, F14. There is a third place winner as well. And that is a half full sublevel. So if you can get a half full sublevel, think of lines, and every line has an up arrow, just one arrow, and every line has one, and they're all pointed in the same direction. That's like the third best place to be. So that'd be S1. It's a half full sublevel. P3, right? Because P can hold 6, so half full is P3. D5, it's a good place to be. And F7, that's a half full F block, F7. So those are the third place winners. Everything else is a loser, doesn't matter. Nothing else counts. Everything else is an equal loser. You are either first place, which is best, second place, or third place. Everything else is equally bad. So it's not like you can say, well, we're at F6 and that's really close to F7, so you're close, you're better than F2. Nope, 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 nope. Everything else is a loser. All right, so in order to achieve these stable configurations, we have 5 elements that are allowed to break the rules. Break those rules we just learned about. You don't have to memorize these 5 elements. They all have something in common. They have 2 things in common, or 2 things that they have in common. So let me write them down for you so you know what they are. Cr, it's chromium, and Mo, it's molybdenum, as well as copper, silver, and gold. So those 5, again, if you want to memorize them, go for it. But here is the trick. Here's chromium, here's molybdenum. See how they're in the same family, in the same row there? How about copper, silver, and gold? All in the same row right there. So if you can remember that, we're halfway there. Help you out here. So we'll start with these guys with pencil lead. We'll start with those guys. We'll take a look at copper. I'm going to do the electron configuration of copper. Silver and gold are pretty long. We'll get the same picture by looking at just copper. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. All right, so here's the important part, that D9 right there. Copper is D9, so is silver, and so is gold. All of them are going to end in D9. And actually, I think this one should as well. I just don't work with them very often. But these guys all end in D9. So these are your D9 group right there. Let's take a look. I'm just going to look at this part of the orbital notation. So not the whole orbital notation. I don't want to, I think you guys understand the 1s, the 2s, 2p, 3s, 3p. Let's just take a look at these 2 parts right here. So that line, 4s is filled up. 5 lines for the 3D. Again, go up arrow, up arrow, up arrow, up arrow, up arrow. Come back and start to pair them up. That's Hund's rule. And hopefully we're seeing it. Look how close, just 1 arrow away from having a full sublevel, a D10. Right now, he's a loser. D9 is nothing special. They're all equal losers. So we're so very, very close to having that stable configuration, that extra electron. So what's going to happen is we're going to pull this electron here and bring it over there. So we're going to end up with a configuration that looks like this. Just 1 arrow there in the 4s. The 3D is filled up. Hey, this isn't that bad. So here's that arrow that we moved right here. This isn't that bad. Remember, S1 is still winning. It's not the best winner, but it's better than nothing, which is where we were right here. This was absolutely losing. That was D9. Now we have D10 and S1. These are both winners. So because this is a much more stable configuration, even though we took an electron, we broke Aufbau's principle, we put an electron in a higher energy level, this is a more stable configuration. So we're going to go with this. This is what happens, which means we actually finish this one off by saying 4s1, 3d10. And that's our exception. That's our broken rule. And like I was saying, guys, you do not need to memorize this, because all you really need to memorize is that you should never end with D9. D9 is like poison. D9 is really, really bad. Doesn't work. Does not work. So if you ever end in D9, know that you need to go back, take an electron from the S, make it 4s1, move it over so that you have D10. Same thing with this other group, chromium and molybdenum. And I'll do the Notation for the configuration, excuse me, for chromium. Go to the smaller element. Won't take quite as much time. 1s2, 2s2, 2p6, 3s2, 3p6. Then we go to 4s and 3d4. So this guy ends in d4. Guess what? Molybdenum also ends in d4. So here's D block. He's in the 4th energy level, and it looks like the 5th. But remember, D block is a level behind. So 41, 2, 3, 4, D4 is molybdenum. So these are the 4, nope, it's not the 4 D4s. Could be any number, but anything that is D4. So there we go. Just like we looked at before, when we do our orbital notation, here's 3d4, and it's a nothing. It's a loser. That is not a very stable configuration. They're all equally unstable, but look how close he is to having a half full sublevel, to being D5. He's so very close. So once again, we're going to take this electron right here out of 4s and put it there. And just like we had up above, we're going to have one electron in the 4s. And although it means we brought an electron to a higher energy level, which breaks the off-ball principle, we now have 3d5, and that's a much more stable configuration. With an S1, D5, that's a winner. So what we're going to see here, again, is not 4s2, 3d4. We're going to see 4s1, looks weird, 3d5. So once again, you don't necessarily have to memorize chromium and molybdenum. What you should work to memorize is that D4 will never happen. Do not end with D4. So those are our two exceptions, the D9s and the D4s. So kind of watch out for those. And again, it should be like poison. If you end with D9, you end with D4, know that you did something wrong. Go back and take a look and make sure that you got it right. All right, well, hey, that wraps up our quantum mechanics unit here. So we got a test coming up. Make sure you guys take a look at the last homework and the test review, and we'll see you next time for the test. Adios.